Hey guys, welcome back. Let's review our unit over statistical inference for proportions. So if you remember our C-fans example with aspergillosis, wow, I can't believe I said that and remember that. But anyway, if you remember, we went around in the Las Res Reef near the Yucatan and south part of the Gulf of Mexico, if you remember that. Anyway, we went around, we randomly sampled, dove down, randomly sampled 104 of these C-fans to see what proportion of them were infected with this disease. So let's say that we thought that the proportion used to be 50%, and we want to see if it has increased, if the problem's getting worse, or if it's better than it was before. So that'll be how we test our hypothesis. Well, the first thing about inferences with proportions that we want to go over is actually kind of reviewing the central limit theorem. So remember, we transitioned from the binomial distribution into sampling distribution models for proportions, and it was a really easy transition. The way we did that, we looked at like the binomial model, and whenever we have like a 50-50 like proportion, like flipping a coin, and sample sizes of 10, these are all the sampling this is a sampling distribution model of all possible samples that we would expect. So the most common would be 50%, which would be 5 out of 10. Having 1 out of 10 or 9 out of 10 would be very unusual. We know all samples vary, but small samples vary greatly. So as the central limit theorem tells us that even if our distributions are skewed or unimodal or bimodal, multimodal, or uniform, or anything like that, they'll all become more nearly normal as the sample sizes increases. That's the central limit theorem. Now, the problem is not with not necessarily binomial expansion, which is always going to be unimodal. It can be skewed though if it's too close to one of the sides though. But anyway, what ends up happening is we take the p times q times n, but we ended up in the square root of that for the binomial, but we divide that by n when we're dealing with proportions, because everything is just going to be divided by the number of our sample size. So for instance, for proportions, if we out of 10, everything's just divided by 10, and so it's easy because we just move the decimal. It's like a tenth of all this stuff, right? So that would be how we convert it to proportions. So that's not really that big of a deal. Now, whenever we take larger samples, so this time we have a larger sample, our sample size is out of 25. So we notice our standard deviation is going to shrink. If we actually calculate the standard deviation here, it actually goes down to about 2/3 of what it was before. If we increase our sample size even larger to a sample size of 100, so this is 10 times the sample size as the original one, you can notice that our standard deviation is shrinking even more. And now we have half of the standard deviation of what we had before for our sampling distribution model. So the central limit theorem essentially tells us as our sample size increases, then which is basically this n here, the standard deviation is going to decrease by the square root of n, 1 over n in that case. So in this case, whenever we quadruple our sample size, that's the square root of n would be half the standard deviation of what it was before, and that's why I went down from 0.1 to 0.05. All right, so that's kind of nice, kind of helpful. So we want to answer the question, what is the true proportion of C-fans that are infected? From our sample, we want to do inferential statistics and come up with a confidence interval we think the true proportion is. We could also test a hypothesis, whether we thought that it got worse than the year before. So let's say the year before we thought it was 50%, that would be denoted as P naught. So we are hypothesizing the true proportion is 50%. The P hat tells us it's from a sample. So in this case, we had 60 out of 104 C-fans that were infected. Now, as long as these are randomly sampled, we should expect that they're going to be representative of all the C-fans in the area. We can't just do a convenient sample of all of them in one area, because that would truly not be independent either, because if this is contagious, then if you find a bunch in that area, then they're more likely to be, the ones around it are more likely to be infected as well. So in this case, our sample proportion, 60 out of 104, was 57.7%, which does seem to be that there's some slight evidence, at least, that that is higher than it used to be. Now remember, all samples vary, smaller samples vary greatly, so this is a small sample of 104. So the next question we need to ask is, what is the sampling distribution model for our sample proportion? So if we had sample sizes of 104, then we would find the standard error based on our proportions which we had, which would be p hat and q hat, which would be 0.577 and 0.423. And then divide it by 104 and take the square root of that, which gives us about almost 5%. So whatever the true proportion is, it looks like we would go this almost 5% for each standard deviation. Now the sample proportion is going to vary within that value, right? So 68% of the time be within one standard deviation of the true proportion, 95% roughly about 95% would be about 1.96, which is just another critical value, right? Within that many standard deviations from it as well. Okay, so that's what's going on. We know our samples are going to vary. We know how much they're going to vary, and from that we have a certain level of confidence that they'll vary within a certain amount within the margin of error, and that's where we come up and write our confidence interval. So the whole idea is that, let's say the big pot is all the possible CFANs that exist, all these CFANs that exist in a loss rose reef. And the true proportion is some unknowable value that is constantly changing. It changes from year to year, even changes from minute to minute as the infections spread, or as CFANs die, or as CFANs are reproducing, healthy CFANs are reproducing. So this proportion is changing all the time. And all possible CFANs, or all possible M&Ms in this case, would be the true proportion. Okay, so that's using the Greek letters. The Latin comes from the sample. We also denote those with the hat symbol over it. So our p hat is going to be our sample proportion. That's going to vary from sample to sample. If we take a different spoonful, we're going to have a different proportion, right? If we take a different sample, we go different places, or a different time, a week later, we're going to get a different value, even from a different random sample. The question is, was it a random sample? So do we think it's going to be representative? So our sampling distribution model for our sample, which was our p hat of 57.7%, has a standard error. Now the standard error is coming from our sample proportion, it's called standard error because it's not coming from the true proportion, it's coming from our sample proportion, which we know has error in it because we know it's varying about 5%. So that's going to be 0.4 or 4.9%. So to create our confidence interval, we know that it's going to vary. It's going to vary from the actual true proportion. So we create a confidence interval which goes a certain margin of error from our sample proportion in both directions, and we believe that it would capture the true proportion with a certain level of confidence based on our critical value. So our critical value is going to be 1.96, I believe, or 1.95. I think it's 1.96 if we're going with 95% confidence. So we're going to center it at our sample proportion of 0.577 plus or minus our margin of error, which is going to be our critical value times whatever our standard error is going to be, and then we add and subtract that from both. We can also put this in the calculator as well to get the exact same thing. We just go to stat, arrow over to test. We'll go down to beta, or Bravo, B as in Bravo, nope, A as in Alpha. One proportion Z interval, so we are doing sample proportion. We had 60 out of 104 CFANs infected. We want to do 95% confidence. Then we hit calculate. It'll give us the exact same values. A little bit rough because I rounded some values here, but you get the idea. That'll give us our confidence interval. We interpret that we're 95% confidence the true proportion is between those two values. So we know that our actual sample proportion is going to vary within essentially two standard deviations 95% of the time. So that means but we don't know where our sample proportion is. So that means if our sample proportion was right on the edge of that, so would also be on the edge of that, the lower edge this time, the true proportion. So that's essentially what's going on here. If it was varying on the low end, let's say it was beyond what we would have expected 95% of the time of our samples, then that means that we would have failed to actually capture within the margin of error the true proportion on that sample because it was beyond the normal 95%. So that 95% can be viewed from both directions, essentially, is kind of what's going on with our confidence interval. And while we have 95% confidence that the true proportion would be within the margin of error for this for this sample. All right, so our random sampling condition, essentially random sampling makes sure that our sample is representative of the overall population. So we have to make sure that our sampling frame, which is what we're actually sampling from, matches as best we can the actual true population. And so as long as it's a random sample, it should be representative, even though we know that all random samples are going to vary based on the sampling distribution model, based on the laws, and essentially the probability of the binomial theorem, binomial expansion, the binomial model divided by the actual number, which is how we got the sampling distribution model for proportions in the first place. All right, so that's pretty much it. Independence, 10% condition. So as long as we're sampling without, when we're sampling without replacement, it's not actually independent, just like cards, like we talked about millions and millions of times. But as long as we're sampling less than 10%, the overall changes that we're going to see in the proportions are not going to be large enough to change our final conclusions. So we can override the independence assumption with the independence 10% condition. Our success failure condition makes sure that our sample sizes are large enough for it to be appropriate for us to use normal models, bell curves, instead of binomial models. We need to make sure that we're not cut off within 3 standard deviations by the hard left bound of 0 or by the hard right bound of n, whatever our largest sample is, our number of our sample size. So we need to expect at least 10 successes and 10 failures. That comes from needing 3 standard deviations, the mean to be at least 3 standard deviations away from both. We plugged in n times p, and then the standard deviation for the binomial model, which is the square root of n times p times q. We were able to take the square of both sides and then subtract n times p, or np, or divide np from both sides, leaving us with np is equal to 9 times q. The largest q would be 1, which would be a failure of every time of 1. So therefore, we need n times p to be larger than 9. So therefore, n times q also needs to be larger than 9 in order to guarantee 3 standard deviations unobstructed. So on the low end, we need to make sure we have a mean which is expecting at least 10 successes to give us 3 standard deviations unobstructed. And on the high end over here, we need to make sure that we have at least 10 failures, so out of 110 failures, to give us 3 standard deviations that are unobstructed as well, guaranteeing that's a large enough, even though it is still going to be slightly skewed for the binomial, that is at least large enough that it's not going to be unobstructed by a hard left or right bound of 0 or n. Then when it comes to hypothesis testing, let's say our null hypothesis is that the years before we believe 50% of all lost artist reefs were infected by aspergillosis. Now we want to know if this year, if the problem has gotten worse. So from our sample, our null hypothesis would be that the true proportion of sea fans that are infected is 50%. The alternative is that it's going to be a one-tailed upper test, meaning that we're trying to see if the true proportion we believe is larger than 50%. In other words, has the proportion increased? So the null hypothesis, this first one here, is going to be based on the assumption that the null hypothesis is true, and that's still 50%. In other words, it hasn't changed from the year before. So that is based on the sampling distribution model of this being 50% with sample sizes of n equal to 104. So if the null hypothesis is true, then it would fill in a sampling distribution model that looks like this. The next thing we need to do is set, as we do millions and millions of samples, right? Next thing we need to do is set is an alpha level. So we default to 5%. Now we can increase our burden of proof to 1% if it's really critical or important. Sometimes we even use 0.1% for certain medical studies, but we also could decrease our alpha level if we wanted a more sensitive test, if it wasn't that important, if we weren't that concerned with false positives. For instance, like for cancer screenings and stuff, we don't want to accidentally scare people, but we want a sensitive test so that we can do more tests and make sure that people that have cancer actually get the treatment that they need. So we would be as concerned as a false positive. Again, nobody likes any type of error. We might set a more sensitive test of an alpha level of 10% in that case, but we usually default to 5%. So the thing is that 5%, whatever we select the alpha level or the level of significance, that's what we need our burden of proof to be. So we would need beyond, if we do 5%, it looks like we would need beyond 58% from our sample size, sample proportion, in order for us to be able to determine or be able to have enough statistically significant evidence to be able to reject the null hypothesis in favor of the alternative. So let's say that they're actually, that would be a false positive, by the way, if we were wrong. That would happen 5% of the time, so we do have to be careful about that. Calculating the probability of the type 1 error is directly equal to the alpha level, so that part's pretty easy. And it doesn't change. Whatever your alpha level is set to, that's the probability of a type 1 error, because we have a set hypothesized null, which is pretty easy. So it makes things nice. Now, the other part that gets kind of nasty is the type 2 error, and that has to do with if the true proportion actually is not the hypothesized 50%. So that can be anywhere from 50.001% all the way up to something really extreme like 70%. So the difference between the hypothesized proportion and the true proportion is called the effect size. So the larger the effect size, like this 20% difference that we actually have here, so just depends on how bad is the infection, right? So if it's 20% more than what it was last year, we should be able to detect that. But if it's only grown by 2% more, so it's like 52%, then we're probably not going to be able to detect that with such small sample sizes. In fact, it looks like only about maybe 10 or 15% of the time we would be beyond the 8% difference from our samples to be able to detect that. And that would be pretty unusual. I mean, on average, most of the time we would expect only 2%, right? If there was truly only a 2% difference 2% difference in the rates of infection from last year. So that's going to need to be pretty high for us to be able to reliably detect that. But we still would be able to detect it, maybe 10% of the time. But that means 90% of the time we would fail to detect it, which would be a type 2 error. So type 2 errors are failing to detect a change. If the effect size is too small or the sample size is too small for that certain effect size, then we won't be able to detect it. Now we can even detect a 2% or even a 1% increase or 1% difference if we have a large enough sample. Now, of course, that would take, a sample size of 15,000 C-fans or something like that to be able to do that. And at that point, maybe a 1% difference might be statistically significant, but it might not be practically significant that we're going to spend all the time to find that, and then are we going to be able to spend all the money to do anything about it if it was just increasing by 1%. All right, so let's say that we actually had a true proportion of 60%, and then we had to find above 58% from our sample to be able to detect that. It looks like we would have been able to have the power of the test to be able to detect that difference of at least 8%, or that difference of getting at least 8% on the 58% from the sample about 70% of the time. So on the bottom part here, that would give us the power of the test to properly be able to reject that null. Now on the bottom here, this is going to be our confidence interval that's centered on our sample proportion. So we can also test hypothesis with confidence intervals. So let's say that we had from ours was centered at 57%, which is about right here. Okay, so about 57%. So I'm guessing about right there. So if we do a 95% confidence interval, within the margin of error, 95% of the time we would capture the true proportion. Now, within it looks like on the very edge of that would actually contain the 50%. So because 50% is contained within our confidence interval, it would be within the margin of error. We would have inconclusive evidence. We would not be able to reject the null hypothesis based on that because it's right on our significance level. Now, if we increased our alpha level to our significance level down to 10%, then now we could do an 80% confidence interval, which would have 10% alpha on one side. Then all of a sudden it would be small enough to be able to reject the null hypothesis. So essentially that's how all that works here. Now this is what's actually going to be varying. So let's say the true proportion is centered at 60%. This is what's going to be varying. It's going to be varying within this this distribution right here. So there will be times that we are over here and we fail to reject it because 50% would be within our margin of error. Now we would have to take we would have to have points that were above this significance level, and also we create our confidence interval based on the alpha level that we want. So if we have a 95% confidence level and we're doing a one-tailed upper test, then on this tail here, which would be when we would have a false positive, I believe actually be on the upper tail here, we would have a 2.5% alpha level. So if we were doing a one-tailed upper test, we would probably do a 90% confidence interval. That way we would have 5% on one side on one tail. So that's why we have commonly do 90% confidence intervals, 95% and 99% confidence intervals, because that corresponds with the levels of our alpha levels of significance of 10, 5, and 1%, by the way. All right, so quite a lot going on here. Hopefully you understood what was going on. You can see it working out. So our confidence intervals, the true proportion is actually remaining constant the entire time. The confidence that we're talking about with confidence interval is for that individual sample. Like 95% of those samples would successfully capture the true proportion within the margin of error. So it's our samples that are varying. The confidence interval is just a process that we create in order to give us a certain level of confidence that we've successfully captured it. So if you notice here, there are times when we failed to capture it. So we failed on that one. It looks like all of these captured. That one failed because this one was more than our critical value away from it. It would have failed as well. But 95 or 10 or 90%, whatever level of confidence we're using, that percent of confidence intervals would successfully capture within the margin of error the true proportion. So again, our population proportion is going to be remaining constant. That is some value that's going to remain the same. It's our samples that are going to vary from sample to sample, varying somewhere along our values. So from our sample, which is our best estimate, we create our confidence intervals, which will successfully capture the true proportion, whatever percent of time, depending on whatever percent of confidence we use for a confidence interval. All right, so let's go ahead and get started. I'm going to do the odd problems from the homework with you. Try to keep this brief. So number 12, these two are pretty similar to each other, so this shouldn't take very long. Vitamin D in 2012. In 2012, the American Journal of Clinical Nutrition reported that 31% of Australian adults over the age of 25 have a vitamin D deficiency. Data came from an ASDIAB study of 11,218 Australians. Does data meet the assumptions necessary for inference? So 10% condition if it's not an experiment. So if it's an experiment, we're looking for independence to make sure that there's random assignment of the treatment groups. That'll make sure that they should be independent of each other. But whenever we're randomly sampling, we need to make sure that we don't sample more than 10% because we're sampling without replacement. Otherwise, we'd violate some independence. We get in some issues where all of a sudden we'd have to do some different methods to be able to, some different high-level statistical methods would come into play at that point. So our sample is certainly less than 10% of all Australian adults, so we're fine. Randomization condition, was it a random? The randomization for sampling is random sampling. Randomization for experiments is random assignment of treatment groups, like we talked about yesterday. So they do not tell us it was a random sample. So hopefully if the American Journal of Clinical Nutrition is doing it, that they're actually doing a random sample. They just didn't tell us about how they gathered the information. So we might question whether or not this sample is representative. So if these results really can even be, if they're useful, if it was a convenient sample or voluntary response bias, there can be a lot of things that come into play if it's not a randomized sample. We shouldn't expect it to be representative. Independent groups, that's if we're comparing two groups. So on this one, they told us about Australian adults. The American Journal of Clinical Nutrition is doing it. So I would wonder, are we comparing to see if we think that vitamin D deficiency is worse among Australians or worse among Americans, or just different? So are we comparing a random sample of maybe 1,200 Americans over the age of 25 to a similar sample of Australian adults or something like that? So we're not comparing two groups. We're not also comparing groups over the age of 25 or over, or those who are younger than 25, if we want to see if it's different among age groups or anything like that. So because we're not comparing groups, we don't have to worry if the groups are independent of each other. That's something that we do for comparing groups, like two proportion statistical inference. Success failure condition, we want to know, do we have at least 10 successes or 10 failures? Are our samples large enough to use bell curves? If we do n times p and n times q, 31% of this is certainly more than 10 Australians, or 10 in our sample that had the vitamin D deficiency, and certainly 69% of this would be at least 10 that did not have the deficiency. What would we like to know in order to compare? Maybe we're comparing against younger Australians that are younger than 25, or against American adults. So I would like to know that in order to be able to compare it if we were going to do comparative statistics, which is more fun, I think. Creating a 95% confidence interval. So to do that, we put it in the calculator. So we go to stats, arrow over to test. We're doing a 1 proportion z interval. Not a 2 proportion, that would be more fun, but we don't have another sample to compare it against. We want to do 0.31 times our sample size, which is 11,218. That was a rounded value, so we do need to round it up and get rid of we can't have 0.58 of an Australian. All right, out of 11,218, and they wanted 95% confidence. Okay, so that's our confidence interval. There we go. Just wrote it down here. Interpret the confidence interval in context. So we're 95% confident that the true proportion of Australian adults over the age of 25 that have a vitamin D deficiency is between these two values. Notice because this is a fairly large sample of almost, well, more than 11,000, we have a pretty small margin of error of about 1%. So we're 95% confident the true proportion of Australian adults over the age of 25 have a vitamin D deficiency are between those two values. Explain what that 95% confidence means. That means that the true proportion is within the margin of error of 95% of samples or confidence intervals created from their samples using these methods. So 95% of intervals would successfully capture the true proportion. Is another way of saying that the true proportion is within the margin of error of the confidence interval. Number 24 is a very similar structured problem. So Rutgers University study released in 2002 found that many high school students cheat on tests. Surprise, surprise. I too have found this to be true in my 5 years of teaching. The research, that's probably the largest discipline issue that I have, is addressing cheating. The researchers surveyed the random sample of 4,500 high school students nationwide. 74% of them said they had cheated at least once. Wow, that's frightening. At least once. I hope it was only once. All right, check the appropriate conditions. 10% condition. So we want to know if our sample size is large enough. If we have 75% or 74% of this sample, then there's at least 10 who did and 10 who said that they did not. So at least 10%. Oh, sorry, we're sampling less than 10%. I was doing the success failure condition. Whatever. All right, less than 10% of all high schoolers. That's certainly true. There's more than 45,000 high schoolers, so we're good. Randomization, they said it was a random sample, so it should be representative, and it was a nationwide random sample. It wasn't just one state or something like that, so it should be representative of the situation nationwide. Of course, it could be worse in some areas and better in other areas, but they're doing national. Independent groups, we are not comparing two different groups. We're just looking at high schoolers. We're not comparing high school to middle school. We're not comparing Oklahoma to Alaska or something like that. We're not comparing two different states. So independent groups, we're not comparing two groups, so we don't have to worry about that. Our independence has to do with the 10% condition. In this case is what we're looking for. All right, create a 90% confidence interval. So again, we'll just put this right in the calculator. We'll go stat test. The hard part's really interpreting it anyway, not just putting it in the calculator. They said 0.74 out of 4,500. So that's a nice value. It's not rounded, so we don't have to change anything. Out of 4,500, we want only 90% confidence. So there we go. There's our 90% confidence interval. I just copied it down. Interpreter interval, we're 90% confident that the true proportion of high schoolers in America who reported cheating on at least one test is between those two values. All right, explain what 90% confidence. So the margin of error, the true proportion is within the margin of error of 90% of samples. So the true proportion would be within the margin of error of 90% of samples, exactly what I just said. Would a 95% confidence interval be wider or narrower? So in order for us to increase our level of confidence, we'd have to increase our margin of error, which means it would be a wider interval. So wider, we must have a larger margin of error in order to have more confidence without increasing our sample size. All right, so not too bad on the time. We went over a lot of stuff. If you notice, I did not talk about comparing two groups and two proportional inference because we just did a whole, that was the last video. So hopefully you guys are current on the homework. You will want to make sure that, and make sure you've done the practice test, which we did on last Friday, or at least it posted last Friday. So we will take the test in class the second day that you guys are in person, so whether it's Tuesday for the A group or on Friday for the B group, and I'll also post it on Friday after school for the students who are taking it at home. So if you have any questions, make sure you ask, and I'll see you later. We're almost done. We got 2 more units, really one more big unit and then a really small short one, and we'll be ready for the AP test. So I'll see you guys later.